going to share the slide so you guys can see it. And let's see, where are we? Now what I need to do is turn off the button on the other side. It's a little complicated, but then I get it right. It's okay. And then let me see if anybody else needs to be promoted. Matthias. I'm going to promote Helen. I'm going to promote Helen as well to be, if you remember Helen. I'm going to, promote the panelist. And oh, Martin here. Okay, I think now did I promote Martin? Okay, good. So I think we have everybody here now. So let me begin the meeting. So welcome everybody back to the online SPICE and SPIN+X seminars. We have here today Ulrich from Zuelicke from New Zealand, originally from Germany, as you can imagine from the name. So just as usual, the Spin Phenomena Interdisciplinary Center has been the collaborative center SPIN+X, led by Martin Schliemann, Burkhard Hillebrand, and Matthias Chloe. And our center are leading these seminars. It is a webinar format, meaning that during the talk, the attendees can only see the talk and the speaker. And please write your Q&A during the talk such that I can then afterwards find you and give you the microphone so you can ask your questions directly. As usually they are at 3 p.m. except on the weeks that we have workshops ongoing, because our staff will be busy with that and the Zoom will be. And just the next one will actually, so next week in this case will not be one because we have a workshop and you're welcome to sign up for that as well. And the 25th we'll have another one from Claridonini. Yeah, so today it's my pleasure to introduce Ulrich Zuelicke. He actually got the PhD in the same institution and advisors as I did, or co-advisor, in Indiana University. So we've known each other for a quarter of a century. He went to a postdoc to the University of Karlsruhe, and from there became associate professor at Massey University in New Zealand, where he's been now. I think now he's in Wellington. He moved there from 2012 to Wellington. And has been very successful ever since. And he is a fellow of the New Zealand Institute of Physics and principal investigation with 3 New Zealand centers of research excellence, and within New Zealand, a driving force within the condensed matter community. So it is with that, I'll stop here, and then I'll ask you, Ulrich, to please go ahead and share your presentation and start your talk.
Thank you very much, Jairo. Thank you for the nice introduction. Hello, everybody. It's great to have the chance to connect with you via this platform. It's a great pleasure to be part of that. Let me just arrange my windows here properly. Thanks very much. Here we go. Yes, thank you for being here to hear me present our recent work on antiferromagnetic order and magnetoelectricity of 2-dimensional charge carriers. This work was done in collaboration with Roland Winkler, who I believe is among the participants of this webinar. And for those of you who might be curious to find out more about details of our work and aspects of our work that I won't be able to cover today, I encourage you to have a look at our just recently published article. Here's the outline of my talk. I would like to start by giving an introduction covering the basics of the magnetoelectric effect. and also remind you about how we create two-dimensional charge carriers in semiconductor quantum wells. I'll then introduce the theoretical framework that we use to describe the new effects that are exhibited by these quasi-two-dimensional charge carriers, namely the multiband envelope function theory for the semiconductor band structure that is describing the host materials in which the semiconductor quantum wells are realized. We are focusing on zinc blende structures that are ferromagnetic, for which the description is quite established. But in the context of magnetoelectricity, we also were particularly interested in antiferromagnets, in this case, diamond structure antiferromagnets. And for those, we actually had to develop the extension of the envelope function theory that describes such systems. After introducing this formalism, I will focus on describing magnetoelectricity that is exhibited by the quasi-two-dimensional charge carriers. Turns out that the effect is tunable by the system characteristics, and it is sizable, where electric field-induced magnetizations reach values of about 1 Bohr magneton per charge carrier. And digging deeper into why this magnetoelectricity is actually occurring in these systems, one finds that it is fundamentally due to the antiferromagnetic order, type of antiferromagnetic order that is present among the charge carriers. And to understand this further, we studied the origin of that order and how also it can be signaled and quantified. And we introduce a new quantity, tau, which is essentially the antiferromagnetic analog to the spin polarization that is generated for charge carriers in ferromagnets. And at the end, I'll present my conclusions. So let's get started with the introduction. I want to first talk about the magnetoelectric effect. Magnetoelectric media are media that exhibit an unusual electromagnetic response. So normally, if one applies an electric field to a medium, what results is an electric polarization. And if one applies a magnetic field, one expects a magnetization to be the response of the system. However, in a magnetoelectric medium, one actually has a situation as shown here. One applies a magnetic field and the system gets polarized electrically. So there is a contribution to the electric polarization that is proportional to the magnetic field. Similarly, if one applies an electric field, currents are generated or spins are aligned such that a magnetization results. So there is actually a contribution to the magnetization that is proportional to the electric field. Now, these kinds of crossover responses, the magnetic field-induced polarization and the electric field-induced magnetization, actually have the same susceptibility governing it. So the prefactor here is the magnetoelectric tensor alpha, and it appears in both contributions for the magnetic field-induced polarization as well as the electric field-induced magnetization. And because these crossover responses essentially couple quantities that behave oppositely under space inversion and time reversal, the electric polarization is odd under space inversion, even under time reversal, and magnetic field is opposite. Similarly, electric field behaves like the electric polarization. Magnetization has the opposite behavior. For this then to be possible, the space inversions and time reversal symmetries need to be broken in the material. And finally, this effect, magnetoelectric effect, is actually an equilibrium phenomenon. So one applies a field and the response develops, and that is an equilibrium state of the system. And so we can describe it in terms of free energy, its dependence on the electric and magnetic fields. And in addition to the contributions that are responsible for ordinary electromagnetism, the energy density of electric and magnetic fields, we have this additional term that couples the electric and magnetic fields and has exactly this magnetoelectric tensor as prefactor. And now one sees that the fact that the magnetoelectric tensor appears as the prefactor of both of these contributions is indeed mandated by this form of the free energy. Why are people interested in the magnetoelectric effect? Essentially, it makes it possible to use everything that in ordinary electromagnetics is only possible by applying one or the other type of field, electric or magnetic, you now can achieve with either one of those fields. And that, of course, doubles or even multiplies the number of experimental knobs one has to manipulate transport, manipulate electromagnetic responses, and so that, of course, interests people for possible applications. Also, it is quite interesting from fundamental points of view. For example, if you put a charge in a region of space on top of a magnetoelectric, then you do not only induce an image charge, and then you find the overall electric field and it's generated from those two electric charges, but you also actually induce image magnetic monopoles so that from the outside you actually have a magnetic field present that looks like as if it originates from a magnetic monopole that is inside the material, and also vice versa. And any type of effect that you know of is driven by one of the electric or the magnetic field now has a dual effect, which allows the ponderance of interesting new device architectures that people have discussed in various contexts. So both from a fundamental and an application point of view, magnetoelectrics are interesting types of materials. Now, let me just quickly survey the types of materials and the magnitudes of the magnetoelectric effect in them. The paradigmatic magnetoelectric material, in fact, the material in the context of which this effect was first discussed, is chromia. And in it, the magnitude of the magnetoelectric tensor components measured in units of the vacuum impedance is actually quite small. And also the magnitude of the magnetization that can be generated or induced by reasonable values of the electric field is very small, measured per particle. However, there are materials where the effect is much larger, and in single-phase materials, the record holder is this terbium compound, 2 orders of magnitude higher magnetoelectric tensor components magnitude than chromium, and a really sizable electric field-induced magnetic moment per particle that can be induced. Now, the real sort of interest for studying magnetoelectric effects actually came about with the discovery of multiferroics, which show really gigantic magnetoelectric effects. And I'm also showing you here the current record holder, which is this heterostructure of a ferroelectric BTO, ferromagnetic iron compound, and it has a huge enormous magnitude of the magnetoelectric tensor components compared with the single phase that is reached in single phase materials, and the magnetic moment per particle that can be induced by values of electric field that can be applied is interestingly of the same magnitude, large, of the same magnitude as the record holder among these single phase materials. Now, also, I want to mention another class of materials where the magnetoelectric effect occurs, even though it is not always discussed under that exact sort of term. So in magnetic semiconductors, the magnetism is mediated by the charge carriers in that semiconductor. And because their density can be adjusted in a field effect structure by a gate voltage, one is actually able to change the magnetization via that gate voltage. And so that is essentially then an electric field induced change in the magnetization, which is a magnetoelectric effect. So one can understand it that way, and the corresponding magnitudes for the effect are as given here. Reasonable value for the magnetoelectric tensor components, not huge, but certainly bigger than chromia. And again, sizable magnetic moment per particle that can be induced by the electric fields that are possible to be applied in such a field effect kind of setup. Now, what I want to make clear at this point is actually an important distinction in the context of using electric fields to control magnetizations and magnetic fields to control electric degrees of freedom. There is sometimes language that is used rather liberally between describing things that are actually different. I just want to make clear what we are actually focusing on in our work. I want to juxtapose the magnetoelectric effect that we are looking at, which, as I just described, is basically associated with electric fields inducing magnetizations. There's another type of effect known as the Edelstein effect, where one drives a current through a system and a transport current through the system, and the magnetization results. This is the Edelstein effect, or by just describing this relationship, also referred to as the current-induced magnetization. Because, of course, a current in a system is typically generated in response to an applied electric field, one can replace the current here in terms of its relation with this transport current, in terms of its relation with the driving electric field, yeah, essentially Ohm's law type of law. And then one again gets a relationship between applied electric field that generates a magnetization in the system. And so superficially, this looks exactly like the relation that is on the left-hand side, where an electric field induces magnetization. Here also an electric field somehow induces a magnetization. But the fundamental reason for why that happens are very different, and the physical situations are very different. And I just want to quickly go through that. As I said earlier, the magnetoelectric effect is fundamentally an equilibrium phenomenon, whereas the Edelstein effect is intrinsically non-equilibrium. It's a transport current that is flowing that generates the magnetization. Furthermore, the magnetoelectric effect is characterized by this property of having a duality between possible electromagnetic responses. Whenever an electric field can induce a magnetization, then there's also the possibility that a magnetic field can induce an electric polarization. Yeah, so this is what we mean by this duality of the electromagnetic responses that are associated with the magnetoelectric effect. The Edelstein effect, as a non-equilibrium phenomenon, of course, exhibits on-Sage reciprocity, I'm sorry. So a current, as I indicated here, results in a magnetization, which in fact also is a non-equilibrium magnetization. So then the reverse is also possible, where a non-equilibrium magnetization that is established in the system can drive a current. This is not the same as the duality that is exhibited by the magnetoelectric effect. Yeah, even though by replacing the current in terms of its expression in terms of the driving electric field, one can have sort of this picture of an electric field inducing a magnetization. However, what will not happen is in the system is that if you apply a static magnetic field, that an electric polarization results. Rather, the reciprocal effect is a non-equilibrium magnetization generating a current. And finally, the symmetry properties for the materials in which the effects can occur is also different. So the magnetoelectric effect, as I mentioned earlier, requires broken time reversal, which means it can only occur in magnets, so in ferromagnets or in antiferromagnets. And the types of materials, their symmetries in which the magnetoelectric effect can occur has been studied in detail and tabulated. For the Edelstein effect, time reversal breaking is not needed because fundamentally we actually couple quantities that behave the same under time reversal. But of course, the Edelstein effect can occur in magnetic materials as well. And in fact, it is very important there to actually make it possible to discuss the phenomenon of, or establish the phenomenon of the spin orbit torque. So what we are focusing on in our work is the magnetoelectric effect, the equilibrium phenomenon, and not the Edelstein effect. And I'm making the distinction because sometimes people talk about the Edelstein effect as a magnetoelectric effect, kinetic magnetoelectric effect. And just to be entirely clear what is really the focus I'm discussing here. Now, let me quickly remind you about how we create quasi-two-dimensional electron and hole systems, which are the material systems that we have focused on in our work. Basically, bandgap engineering in semiconductor heterostructures allows us to realize the textbook example for a quantum well, combining materials with different fundamental bandgaps like aluminum arsenide, gallium arsenide, aluminum, gallium arsenide, creates a spatial variation of the conduction band and valence band profiles, and results in the trapping of charge carriers in that quantum well, which then live in bound states for the motion in that growth direction of the quantum well, but are free to move perpendicularly to it. Now, it's been known for a long time that one can affect the bound state of the charge carriers, the 2D electron and hole bound states, by applied electric and magnetic fields. In particular, if one applies a perpendicular electric field, one probably immediately can envision that this shifts the density profile of the two-dimensional bound state. But also applying in-plane magnetic fields affects the bound state. In fact, it actually splits the density profile in a symmetric fashion. And there have been beautiful experiments done in the SPICE-JGU group, for example, that have explored this. Now, in our context, it will be the coupling of the perpendicular to the quantum well electric field, or the application of an in-plane magnetic field that couples to the bound state that leads to the magnetoelectric effects. So these fields couple to the bound state, and as a result, the crossover responses, namely a magnetization in response to the electric field and a polarization in response to the magnetic field, will realize. So we'll discuss this later on. Now, how do we actually describe theoretically the electric and magnetic responses of the quasi-2D electron systems? Essentially, we solve a Schrödinger equation that contains the symmetric confining potential that describes the quantum well. The electric field is included by the electric potential term. And the in-plane magnetic field is included via the minimal coupling to the vector potential that is associated with that in-plane magnetic field. And then the solution of the Schrödinger equation yields the eigenstates of the quantum well, which are described by the quantum numbers labeling the quasi-two-dimensional subbands and the wave vector, two-dimensional wave vector for the in-plane motion. So it's the combination of plane waves in the in-plane motion and the bound state. And then we can calculate the quantities of interest for us, namely the component of the electric polarization that is perpendicular to the quantum well, by essentially summing up all the microscopic electric dipole contributions from each of the occupied 2D electron states in that quantum well, basically measuring the displacement, or this is basically the displacement of the bound state in the growth direction. And also for the implementation, contributions are added up for all the occupied states in the 2D electron system, namely their orbital magnetization contributions, which are essentially due to currents that are orbital currents that are flowing, equilibrium currents that are flowing in the system, and spin components associated with the expectation values of the spin degree of freedom for these particles. Okay, now when I say that we solve a Schrödinger equation and find eigenstates, then we of course do not solve the simple, you don't use the simple Hamiltonian with the parabolic sort of p²/2m dependence that applies to electrons in vacuum, but we actually solve the Schrödinger equation that describes properly the charge carriers in the semiconductor host materials that are used to make the quantum well. And for that, we use the envelope function theory for such charge carriers. And I just want to briefly tell you the ingredients only for that description. And because that, especially in the context of the antiferromagnets, that actually is one of the important aspects of our work. So before I go into the formalism, I just want to clarify what kind of materials we are actually interested in for the semiconductors that are host materials for our making the quantum well. All of these are systems that crystallize invariance of the diamond structure. Just a brief reminder, diamond structure, two phase standard cubic sublattices that are basically two sublattices that are equivalent, shifted from each other, and materials that crystallize in the original diamond structure are, group 4 semiconductors, silicon, germanium, and this crystal structure, diamond structure, is inversion, space inversion is symmetric because the spatial inversion maps the two sublattices onto each other. This structure is also time reversal symmetric because there is no magnetism or anything in that system. So with both of these systems, symmetry is intact, there's clearly no chance that this material system would exhibit magnetoelectric effects. Now, if one considers a variation on that diamond structure, which is called the zinc blende structure, where one occupies the different sublattices with different atoms, for example, gallium on one sublattice, arsenic on the other, describing 3,5 semiconductors, for example, then this structure actually has broken space inversion symmetry because now the mapping of the two sublattices onto each other via space inversion is not symmetry anymore because we encounter different atoms on each. But time reversal is still a good symmetry of the system. So also the zinc blende structure materials would not show magnetoelectricity. However, if one makes the zinc blende structure magnetic by doping it with magnetic ions, replacing, let's say, some of the gallium with manganese ions, then in addition to the broken space inversion, also the presence of magnetism breaks time reversal, and then this material system actually does have the ingredients for exhibiting magnetoelectricity. And so this is one type of material system that we have considered. Now, the basically purer form of magnetoelectricity turns out to be exhibited by materials that are antiferromagnetic. And so we were interested in using such a materials platform, a diamond antiferromagnet, where on the two sublattices one has opposite magnetizations associated with these sites. So each sublattice is characterized by one direction of magnetization, and these directions are opposite between the two sublattices, making the system a collinear antiferromagnet. And so the space inversion symmetry and time reversal symmetry are both broken in this system. And so this has also all the ingredients for being a magnetoelectric material. So how do we describe the charge carriers in such systems? So for the zinc blende semiconductors, there's a well-established envelope function theory that's called the Kane model that describes the number of relevant bands that are needed to get accurate results for describing conduction and valence band carriers for all types of purposes, including the properties of quantum well heterostructures. And so just showing sort of this picture, don't give you the matrix, 14 by 14 matrix that takes into account these different gap energies and couplings between these bands. The presence of magnetism can be easily included in terms of a ferromagnetic exchange field, which couples to the charge carriers via a Zeeman-type spin splitting. And so that has been applied successfully to describe these materials, which, the zinc and ferromagnetic materials are materials of great interest. And so this theory has been used for characterizing the electronic magnetic properties of the charge carriers. Now, even though this is a sort of multi-band description that is in fact needed, a multi-band description is needed to describe these materials properly. If one is just interested in the carriers in the and states in the lowest conduction band, then one is actually able to derive quite accurate two-band models out of this multi-band description that are tractable analytically and allow one to then get some more physical insight, more basic insight into what is actually going on in terms of phenomena that one is interested in. And that is useful because if one wants to look at other bands, in particular valence bands, then these have such complicated band structure effects that they are only amenable to numerics, be treated properly by numerics. But the understanding that one gains by looking at these analytical models for the conduction band is instructive to also understand actually the relevant physical phenomena here. So it's useful to actually study these two-band models and then get some intuition about what is going on in the system of interest. And this is exactly what we have also done for our magnetic effects of interest. Now, for the, as I said, for the zinc blende ferromagnets, the theory is very well established. But as we are interested also in describing quantum wells made out of antiferromagnetic semiconductors, we wanted to consider this type of material, the diamond antiferromagnet. And for that, the envelope function description was not known, and so we had to basically derive it, and basically this was done by applying the well-known tight binding models for the diamond and zinc blende structures, with now the added ingredient where one has this staggered magnetization associated with the two equivalent sublattices in the diamond structure. Yeah, so there is this staggered exchange field Y, and including that, then one can again derive the multiband envelope function description, the sort of amended Kane model for such an antiferromagnet. And so, in addition to the typical types of terms that exist in such Hamiltonian, one gets additional terms that depend on the staggered exchange field, terms that are not possible in the absence of it. And so the basically derivation of these additional terms is one of the major new results because it yields a model that can be more broadly applied to actually describe the electronic properties of such diamond antiferromagnets. And I'm just sort of in the table giving you a few of those. So couplings between conduction and valence bands that are proportional to the staggered exchange field. And then also one finds contributions to the Hamiltonian describing, for example, the conduction band and the valence band in the following for our band model description of the conduction band, the analytical treatment. This term will actually play a crucial role. So this is the two lowest order in wave vector k, the first contribution to the Hamiltonian of the conduction band electrons that depends on the staggered exchange field. Yeah, so this is what will be important for our analytical model later on. Now, in fact, let me describe now how we can what we obtain for the description of the conduction band in terms of such a two-band model that is amenable to analytical study. Let's start with the ferromagnetic zinc blend material, quantum well realized in this ferromagnetic zinc blend material, host material. So the electrons in the conduction band are described by a Hamiltonian that has various contributions, the usual kinetic energy contribution, the external potential that realizes the quantum well, confining potential. Then the broken space inversion symmetry in the zinc blende material gives rise to this so-called Dresselhaus term, which is a coupling between the orbital motion, the linear wave vector, linear momentum, with the spin degree of freedom of the electrons. And because we are looking at a ferromagnetic zinc blend material, we also have an exchange field coupling to the spin degree of freedom. And in principle, if we apply a magnetic field, that is also subsumed under this sort of Zeeman spin splitting in this system. Now, all these terms together, including also, if we apply it, the electric field, potential associated with the applied electric field, then that is the description of our electrons that are confined in the z direction, which is the growth direction. So we have a confinement problem in the z coordinate, but we have free motion in the directions perpendicular to it in the xy plane. But in this situation where we have this broken space inversion due to, due to the zinc blende structure, giving rise to this Dresselhaus term and also the Zeeman splitting, one actually finds that the dispersion is to lowest order parabolic for the two-band description of the conduction band, but it is not a parabola that is actually centered at the origin, but is actually centered away from the origin at some value of wave vector that depends on the prefactor characterizing the broken space inversion symmetry, depends on the confinement, and is opposite for the two basically majority and minority spins in that system. Yeah, so we have the presence of the exchange field basically forces the spin to be parallel to that exchange field, defining the majority and minority charge carriers, which actually zeros a contribution to that K-naught operator and basically generates this shift of the dispersion, the 2D subband dispersion for the conduction band electrons. So that's the situation in the zinc blende ferromagnet. Now in the diamond antiferromagnet, things look actually remarkably analogous. So again, we have the kinetic energy contribution that describes our conduction band electrons, the external potential And then the term that I pointed out earlier that arises due to the presence of the staggered exchange field. And that superficially looks like the Dresselhaus term, certainly in its dependence on the wave vector, but notice it does not couple to the spin degree of freedom of the conduction band electrons, but to the component of the staggered exchange field. In fact, the spin degree of freedom in the system is a silent degree, just giving rise to factors of 2, because of course in an antiferromagnetic we don't have any spin splitting. Now again, including all these terms, potentially also the electric field, potential associated with the electric field, one has the same structure for that Hamiltonian in the antiferromagnet, again a confinement problem in the Z coordinate and a shifted parabola. And again, the amount of the shift depends on the degree of freedom, strength of the breaking of the term that breaks space inversion symmetry, in this case associated with the staggered exchange field. And also the direction of these, either the ferromagnetic or antiferromagnetic exchange fields enters in the form of this shifted wave vector. Now, armed with this theoretical formalism, we are able to discuss the magnetoelectric responses, and I'll be focusing on the in-plane magnetization that is induced by a perpendicular electric field due to time reasons. So using this analytical form for the this two-band description for the conduction band, we can treat the presence of the electric field perturbatively and calculate, as basically described in the introduction, just adding up contributions of each of the occupied states. We can find the in-plane magnetization, and we find that the application of the perpendicular electric field couples to the bound state in this system where the 2D parabola dispersion, subband dispersion is shifted in such a way that there's actually a finite overall contribution to the in-plane magnetization. And it is proportional to the electric field and various other contributions. In particular, the direction of that magnetization is determined by the ferromagnetic exchange field in the zinc-blende ferromagnet, and characteristics of the quantum well enter in some matrix element. And there's an overall scale that determines how large this magnetization is, and it basically contains the sheet density of the carriers and is tunable via that. And also there are dependencies on the quantum well with various places. Now, you see the two results that one obtains for the zinc-blende ferromagnet and the diamond antiferromagnet. They are completely analogous, except for this contribution, which is basically a number that gives you the degree of polarization of the charge carriers due to the magnetization. So what is the polarization of the charge carriers? Let's say for a fully magnetized system, this is 1. And in the absence of the exchange field, this is 0. So for the fully magnetized zinc-blende ferromagnetic sort of conduction band situation, when we have only majority carriers, is equivalent to the situation of the diamond antiferromagnet. Now, if one puts in the numbers, or in this case also just sort of does the calculation in the more numerically accurate multi-band model, one can find the overall magnitude of the magnetoelectric effect, and finds that for the conduction band, it is actually quite small. So these, what I'm showing you here is the in-plane magnetization that results from the application of an electric field perpendicular to the quantum well for a ferromagnetic system or an antiferromagnetic system where the the exchange fields point in the x direction, and the magnetoelectric effect is signified by having the electric field induce a y component of the magnetization. And the fully numeric results, accurate results, agree perfectly with the two-band model, actually, in this case. But what one sees is that the electric field-induced magnetization for sort of largest possible values of reasonable values of the electric field only reaches sort of this 10 to the minus 2 scale of 10 to the minus 2 Bohr magnets per charge carrier. Magnetic moment per charge carrier is really small, but it is a platform, the conduction band, to understand and describe this magnetoelectric effect in sort of analytical detail, not just numerically, and therefore interesting to look at, even though practically it will not be important. We will see later that for the 2D Hall systems, the magnetoelectric effect is actually really sizable and therefore also of practical importance. But let's stick with the conduction band still and actually ask what is fundamentally the reason why we have this magnetoelectric response. And the physical picture that explains it is as follows. Basically boils down to the electric field modifying the equilibrium current distribution in the quantum wells that are realized in a ferromagnetic zinc blende or an antiferromagnetic diamond structure. So let me go through this in some detail. Let's focus first on the quantum well that is realized in the antiferromagnetic, diamond antiferromagnetic semiconductor, and no electric field applied. And if one looks at the current distribution in the confinement direction, so this is the Z direction perpendicular to the quantum well. And for reference, here also the dotted curve shows the density distribution of the 2D bound state. So this is the bound state associated with the lowest two-dimensional subband in that quantum well. If one calculates the currents, sums up all the currents, contributions of the occupied quantum well electron states, one finds that there is actually a finite current distribution, equilibrium current distribution, that has the shape of a quadrupole. So there's no net current flowing through the system, and there's also no magnetization in the system, but there is this quadrupolar current distribution that is basically like two magnetizations that cancel each other side by side. So that quadrupolar equilibrium current is basically the result of the combination of broken space inversion and time reversal symmetries together with the confinement. That exists in the absence of an electric field. Now, if one goes from the ferromagnet to the antiferromagnet to the ferromagnet, one finds the same situation. One also finds that there is this quadrupolar current distribution. But in addition, one also has a dipolar current distribution, which is simply, however, the paramagnetic response of our quantum well electrons to the ferromagnetic exchange field that is present in this particular system. So, and these two are actually in opposite directions. So we're focusing on the red curve, the quadrupolar one. It's exactly the same type of situation that is realized in this ferromagnetic zinc blende system, also in the absence of an electric field. Now, if one applies an electric field, what happens is that this electric field couples with the bound state, leads to changes in the bound state, which then in principle affects the charge density distribution as well, but that is actually a small effect for these conduction band systems and these values of the electric field. But quite dramatic effects result for the current distribution. So instead of being symmetric around the center of the quantum well, it is now an anti-symmetric contribution, which essentially means it's not quadrupolar anymore, it's quadrupolar plus the dipole contribution. And the dipolar current is associated with a magnetization. So the electric field essentially distorting the equilibrium quadrupolar current distribution, generating this finite dipole. This is the fundamental sort of mechanism for the electric field induced magnetization in our system. And the same happens again also in the ferromagnet, where, of course, on top of that, we have the paramagnetic current dipole distribution, current distribution that is just the paramagnetic response. But so we now have also magnetization perpendicular to that paramagnetic response that is associated with the magnetoelectric effect. So this is the physical explanation for why the magnetoelectric effect occurs in these quantum well systems. Now, as I said, for conduction band systems, that effect is small. But for valence band carriers, it actually turns out to be much larger. So I'm showing you here the magnetic field induced, electric field induced magnetizations for both antiferromagnetic systems and ferromagnetic systems for two different quantum wells thicknesses. And the basic physical picture again, however, is exactly the same as just discussed for the conduction band electrons. So again, in the antiferromagnetic and also the ferromagnetic zinc blend system, in the absence of an electric field, one has quadrupolar current, equilibrium current distributions, which get distorted by the application of an electric field. And now this is a rather dramatic distortion, generating sizable dipolar contributions to the equilibrium current. And that is basically the magnetization that results from the application of an electric field. And that now reaches values of order of Bohr magneton, magnetic moment of Bohr magneton per charge carrier. And in fact is also shows nonlinear behavior as a function of electric field, which comes due to the peculiarities of the valence band structure. Which always has strong nonlinear effects that are the origin of this deviation from linearity that one sees here. But the important thing to realize is the much larger magnitude. So I'm not going into detail sort of why the magnetoelectricity in 2D holes is so strong. Fundamentally, one can say that the asymmetry in the dispersions in the wave vector is the reason, and one can study this in some detail, actually quite carefully. So both in the antiferromagnetic and ferromagnetic situation, if one looks at the energy contours and Fermi contours, one sees this strong asymmetry in the situation without the electric field applied, and then the electric field application of that actually with that asymmetry present leads to this magnetoelectric response. Now, fundamentally, we traced back the origin of the magnetoelectric field induced magnetization to the manipulation of these quadrupolar current, equilibrium current distributions that are present. And so based on that, we were interested in actually understanding more about that there is this antiferromagnetic, underlying antiferromagnetic order of the charge carriers in the superficially ferromagnetic 2D system, for example, in the zinc blend case, but also in the system where antiferromagnetism is also already present in the crystal structure. So we went about to actually understanding and quantifying the antiferromagnetic order of these charge carriers. Of course, to find it, one could just say, okay, let's plot the current distributions, and if one finds quadrupoles, yes, then one has some antiferromagnetic order. But this is not a systematic way of describing this, and so we wanted to find a way to actually describe antiferromagnetic order in complete analogy to how one typically describes ferromagnetic order in an itinerant electron system. So let me remind you, ferromagnetic order manifests for the charge carriers as an exchange field that couples to their spin degree of freedom. So there's this spin splitting term associated with the exchange field. And from that, one sees that the spin operator, sigma, basically satisfies these relations. One obtains it by taking the derivative of the total Hamiltonian with respect to the exchange field. And if the expectation value of that spin operator, the spin polarization, is finite, then one has charge carriers that are ferromagnetically ordered. This can happen now because one has such an exchange field present, but in principle can also happen if one applies a magnetic field, or who knows what type of mechanism or situation gives rise to that spin polarization. Now, in our antiferromagnetic system, the diamond antiferromagnet, we have the staggered exchange field that basically encapsulates the presence of antiferromagnetism in the crystal structure. And for the electrons, for example, in the conduction band, but in general also in the valence band, it leads to additional terms which depend on the components of that staggered exchange field. And that can be written again as basically a scalar product between the staggered exchange field and some vector tau. And that vector tau we call the Néel operator, and it's again obtained by taking the derivative of the total Hamiltonian with respect to the staggered exchange field. And the expectation value of that operator is the quantity that is the toroidal moment. And if it is finite, it signals the presence of antiferromagnetic order, the same way that the finite spin polarization signals an imbalance of spins, basically in magnetization of charge carriers in the system. Now, these operators, their form, sigma and tau, is fixed for any given band structure. Whether or not an exchange field is actually present doesn't matter. So we just use this as a way to essentially tease out the form of the spin operator or the Néel operator. But then if one looks at its expression in terms of quantity, characteristic quantities associated with the charge carriers, that then doesn't depend on the exchange fields anymore. And so these can be used to describe ferromagnetic or antiferromagnetic order in any context, even in the absence of the corresponding exchange fields. So in particular, for our quantum wells, we can calculate it. So we, for our conduction band electrons, we find what this vector tau is, just doing the derivative as I showed earlier. And then one can calculate the toroidal moment of the charge carriers in these quantum wells for the zinc blende ferromagnet and also the diamond antiferromagnet. And in the zinc blende ferromagnet, as well as the diamond antiferromagnet, one finds that it is finite, giving you the expression in terms of Medius elements. The confinement plays a role. Again, the magnetization, presence of the exchange fields, ferromagnetic, antiferromagnetic. And so one finds that antiferromagnetic order of the charge carriers exists in both cases, in the ferromagnetic quantum well as well as the antiferromagnetic one. And characteristics of this vector depend on the presence of the exchange fields, their direction, etc. And basically, that is the finiteness of tau is the indicator or reflection of the presence of these equilibrium quadrupolar currents that I discussed earlier. Yeah? So essentially, these quadrupolar currents can think of sort of two current loops in opposite directions, side by side, which is completely analogous to having staggered spins. So this is a orbital antiferromagnetic order, and it is basically measured and indicated by this this toroidal moment. Okay, so I think my time is about to be up. Let me conclude. We have discussed equilibrium magnetoelectric effects in quasi two-dimensional systems. The magnetoelectricity in these systems results from the interplay of either ferromagnetic or antiferromagnetic exchange fields that are present, the confinement in the quantum well structure, and the absence of inversion symmetry. We have found that the magnetoelectric effects are sizable for the quasi-2D Hall systems in particular, that they are tunable by the system characteristics, by the sheet density and the quantum well width. We have microscopic descriptions of those in terms of the charge carrier degrees of freedom in these systems, and they're experimentally accessible because routinely these days one is able to make high quality quasi two-dimensional quantum well systems. We derived the envelope function description for the band structure of diamond antiferromagnets, basically generalized the Kane model to include the effect of a staggered magnetization on the two sublattices that make up the diamond structure. And now that envelope function theory is more widely applicable than just in the context of magnetoelectricity, which was our focus here, to study the electronic properties of antiferromagnets, in particular diamond antiferromagnets. And we identified the toroidal moment of charge carriers as a indicator quantity that represents antiferromagnetic order and is essentially complementary to the spin polarization to characterize the magnetic order in these 2D systems. So the toroidal moment characterizes the presence of antiferromagnetic order the same way that finite spin polarization signals ferromagnetic order. Now, in the future, we want to consider the magnetoelectricity in antiferromagnetic materials on a broader base, utilizing such envelope function theories to gain a broader understanding of those and discuss possible applications in antiferromagnetic spintronics. And with that, thank you very much for your attention.
Thank you very much, Uli, for a nice, very clear talk. So I think most people they usually tend to raise their hands to thank you, but I think in this case it's better to keep the hands for the questions. Okay, now everybody's in the hands, so keep them down for a second. Let me, I think, Carlo, I don't know if you have a question at the moment, but I'll put you here as the first question, maybe. A second, how to talk. So Carlo, do you have a question for Uli? Because I wasn't sure if Carlo, you can unmute yourself if you want. Maybe from before, actually, so I'm not sure. Carlo, can you hear me?
So I think it was a mistake. So
okay, no problem.
Talk was very good, but I do not have any question. Thanks.
Okay, so Hanshin Wang, you have a question?
Yes, thank you for your nice talk, and from which I have learned a lot. My question is, which parameter will influence or decide the direction of the microscope net magnetization generated by the antiferromagnetic current? Yeah.
Yes, let me try to go back. Yes, so the electric field induced magnetization, so the direction of the in-plane magnetization is given in terms of the direction of the exchange field that characterized the ferromagnetic system or the staggered exchange field that characterizes the antiferromagnetic system. So it's these angular dependencies that basically determine the direction of the magnetic field. The magnetization, it's not just perpendicular, it's complicated. So there's actually, so it depends a little bit on, yes, in which direction with respect to the crystal or one axis, the staggered magnetization points. So basically that that direction is fixed by the magnetization, and yeah, that's basically it. Potentially also, yeah.
Okay, thank you. Thank you.
Okay, I have a question a little bit regarding the systems themselves. So you're proposing in the ferromagnetic, I guess the gallium manganese arsenide version. What is the antiferromagnetic version of? Do you say that you would create these single blend systems?
Yeah. So I as a sort of the let me try to get there. Yes, here we go back. So as a material, so the diamond antiferromagnets at the moment are relatively rare. So there are some. So let's say there are interesting materials that have a diamond structure and have, for example, antiferromagnetism on one sublattice and things like that. So a perfect diamond antiferromagnet like this, an example for that is touted for, being an example for that is this particular compound. So I'm not.
But is this a semiconductor or is it semiconductor?
If I remember correctly, this is an insulator. So yeah, so it is, I think at the moment, I'm not sure how one would sort of realize a material like sort of, gallium manganese arsenide, somehow making such a sort of analog structure from our usual typical 3-5 semiconductors. I think it would have
we had essentially copper manganese arsenide, which turned out to be not a semiconductor, but a good metal antiferromagnet, but which also had, of course,
it's not a diamond structure, right? It's
right. Well, but it's actually two inverted. The copper minus arsenide in this case would have, has the nail order spin-orbit torque. It's analogous to the I think you had here equilibrium property that you were discussing, and we discussed in our nail spin-orbit torque something that is out of equilibrium with these two sublattices that have both inversion symmetry pairs.
Yeah.
And
but if I remember correctly, those were simple cubic lattices, right?
Correct. Well, not simple cubic because they're cubic in a symmetry, but they have formed by two sublattices that each themselves have inversion symmetry with opposite direction. That's the whole point of the stagger one. So
they probably would not, exactly. They would probably not be magnetoelectric for that reason.
No, they're not allowed. This is because there's an out of equilibrium situation in here. My question is now in here: which one do you have in mind for these ones? Because they would, in reality, you want insulators, right? If you want to put an electric field through this thing.
So that's maybe I should say our 2D systems are realized from semiconductors, and yes, so they are would have some type of magnetism and so on, but the magnetoelectricity occurs in this 2D system which is conducting now. So we can have magnetoelectricity in conductors that are low dimensional. So this is one of the interesting aspects of our system. The 2D system is the conductor for the, within the plane, but perpendicular to the plane, it is more like a molecule. So
I think you will have a hard time making for a conductor in terms of the width of these things. You would have a hard time making them, right? That's the problem.
No, so let's say the idea is, so both like for the zinc blende structure and the antiferromagnetic system, the vision is that one uses different types of materials, combines them to make a heterostructure which realizes your 2D system with the magnetism in it, one way or another. And then you have your 2D conductor, to which you can apply a perpendicular electric field, there's no problem. And you generate the in-plane magnetization, which also doesn't generate anything unusual and undefined. And also you could apply a in-plane magnetic field, which is also,
very what I'm saying is that if it is too metallic, the 2D layer, the confined bond layer, if it has too many carriers being metallic, not semiconducting, you will have a very, I think the voltage could kill you. That you would actually need.
Which voltage? Which voltage?
The perpendicular one.
No.
You were not generated inside, I don't think. Maybe I'm wrong on this, but.
You are in that sense focusing on a different thing, I believe. So the 2D system is metallic within the 2D plane, but is insulating perpendicular to it. So you can apply a perpendicular electric field, and you don't do anything drastic. You actually have rather weak.
No, I was referring to the perpendicular field. I don't think. Okay, let's discuss.
So it's not like later, it's not like a thin metallic layer where you now have sort of charge accumulation, on plus minus one either side. No, you have a bound state that you somehow shift, and that is quite rigid actually as far as the electric response of that bound state to an electric field is concerned. But the magnetization response is for the implementation is big. So even though the electric response to the perpendicular electric field of the bound state due to its rigidity is rather small, the implementation that's generated is actually really big, in particular for the holes.
Okay. So Revas has a question that I want to take all the time. Sergio, afterwards.
Hello, and thank you for the inspiring talk. So you spoke of this connection between the toroidal moment and antiferromagnetism, which was something I missed because somehow, like to me, there is this textbook definition of antiferromagnetism that is that there's a modulated, staggered magnetization, right?
Exactly.
So at which moment does toroidal moment come in?
Good. So we can, let's say if we talk about antiferromagnetic, we usually have spins in mind. Similarly with magnets, we always sort of think of spins that are kind of parallel. But you can also represent the spin degree of freedoms, or you can think similarly, instead of spin degree of freedoms, you can think of current loops, which sort of make a magnetization. Yeah. So let's say think of spin not as a spin, but basically a current loop. So associate with some current, or you know, current, sort of a dipolar current distribution like this. So that would make like something equivalent to a spin up. And now then you can think about antiferromagnet configuration as having a current loop that goes sort of in one direction, so in, out, and then right next to it, a current distribution that is a dipole going in the opposite direction, out, in. So, and if you sort of think now of spin up next to spin down, this would be a current dipole in one direction next to a current dipole in the other direction. So this is what I'm sort of showing on this side here. So this is a current loop that goes in one direction next to a current loop that goes in the other direction. And this is like a spin coming, let's say, out of the plane next to a spin going into the plane. So this sort of orbital equilibrium currents are an exact analogy to an antiferromagnetic. So this quadrupolar current distribution is an exact analog for an antiferromagnetic type of staggered magnetization configuration that we know of spins. And so like you have these orbital and spin contributions to the total magnetization. In fact, in a multiband model, all of the magnetization is actually orbital in character. So you can think of basically all types of magnetizations for itinerant charge carriers as being sort of due to some type of equilibrium currents. Now you could look at the currents and see, aha, look, there's a quadrupole and there's a dipole, and so this is a magnetization, this is a staggered magnetization, blah blah. But the introduction of this toroidal moment is basically designed to have a single quantity whose expectation value being finite allows you to say, aha, there must be, this is a magnetically ordered charge carrier system. So if we have a finite spin polarization of our electrons, then let's say this is Pauli paramagnetism of our charge carriers because we have some magnetic field applied or there's an exchange field applied. So we know spin polarized electrons, magnetic order. So what we find is that there's an analog to that in terms of this toroidal moment, which basically says, if that is finite, this basically corresponds to some sort of antiferromagnetic, I don't want to call it polarization because it makes no sense, but let's say just for linguistic analogy, like an antiferromagnetic order, yeah, let's call it that, that is exhibited by the charge carriers for whatever reason, where it comes from in the system. But it's the exact analog of that spin polarization that shows sort of the existence of majority and minority, let's say charge carriers in a magnet. One has an indicator quantity for that. Correct. And so we call this a toroidal moment because this vector has actually the properties of a toroidal vector.
Maybe you could call it nail moment. That would maybe.
Yeah, why not? Why not? Yes. Very good.
So if you don't mind, let me go to Sergio now, and then we can continue afterwards with Sergio. Go ahead.
All right. Hi, Uli. Thank you for a nice talk. I have a question, a simpler question, and that is that because you have inversion asymmetry in the system, so how come your this magnetoelectric coefficient doesn't come in at first order in K? Why do you need third order?
So in a bulk material, bulk singlet material, the lowest order term that arises due to broken spatial inversion symmetry in the conduction band, is of third order.
Right, so but you're at the interface, right? You're making a heterojunction, so you're breaking. You have an interface and you have another asymmetry group.
If I may jump in here, for the quasi 2D system, it is linear in the in-plane wave vector. We are seeing here Uli's formula for the staggered for the Néel term, Uli, the HY on the right hand side, and if we quantize Kz, which is what we need to do for the bound states in a quantum well, it becomes linear in the in-plane wave vector in much the same way that the Dresselhaus term in bulk is cubic, but it becomes linear in the in-plane wave vector when we go from the bulk material to the quasi 2D system. Does this answer your question?
Yes, yes. Although, wouldn't you also have a Rashba-like at the interface?
Oh, sure. I mean, we have in that sense looked at at one term that allows us to work out things very explicitly. Rashba term is present and contributes, but in slightly different ways, actually. So this is also discussed in our paper, how the Rashba term contributes also and adds on. But yeah, in qualitative terms, how things depends on the direction of the exchange field and so forth, that is the same.
Okay. Yeah. But by the way, I had another question, if I may, Jairo, on the coefficient D that you have in there. That depends on material parameters, of course.
Exactly. Band gaps, band couplings. Yep.
So you can so the question, when you arrive at your estimate for the conduction band effect, you made assumptions about those parameters. I mean, is there a way that those can be enhanced?
So
this is connected with the question of the linear effect, right? Because the Rashba-like terms or whatever, the linear will also well, it's a question, I guess. They'll also contribute to make it bigger. Sorry.
Yes. So for so for the purposes of basically the numerical calculations, the band parameters for indium antimonide were used with some value of the staggered exchange field or linear exchange field, ferromagnetic exchange field. So and then that these parameters enter the multiband Hamiltonian and essentially determine the magnitude of D. Yeah. And yeah, one can look into the exact form, how that depends on band structure parameters, and can discuss sort of what one can do to actually make it bigger or smaller. But it comes down to what Jairo's question was about earlier. I mean, for the sake of argument, we include, and for comparison also between the ferromagnetic and antiferromagnetic case, indium antimonide band structure parameters were used, but there is actually no physical realization of antiferromagnetic indium antimonide yet.
Right,
so
that's a problem.
Never underestimate the material scientists. So, but yeah,
of course. All right, thanks a lot.
With that, I'll have to thank you both. Also, I like it. Yes. This is like
thank you, Roland.
I'm like Charles V. But
it was a team talk.
It's a team talk. I was like, SPICE is like the kingdom of Spain during Charles V, that the sun never sets, because Uli is at 4 in the morning in New Zealand. Sergio is also quite early in the US, celebrating the victory from Trump. And we're here in Europe, so I'm also very happy that the sun never sets in the kingdom of SPICE. But thank you very much all for being here once again, and we'll be meeting you in 2 weeks' time. And with that, I'll thank you again. And Uli, one last comment before I leave, because I have to really run. If you put a strain, would you get linear term then? Don't answer yet. Answer it by email. I'll send you an email about it.
Okay. Yes, good. Yes.
Yes, I think you do.
Yes, it must be yes.
I'll follow it up on that. Okay. See you guys.